Hello and welcome back. In this lecture, I'd like to talk about what goes into creating a C program. So there are 4 fundamental tasks in the creation of any C program. And what these tasks are include editing, compiling, linking, and executing. All right, we talked about the different steps that you'll employ when you write a C program in terms of you're going to understand requirements, you're going to design your code, you're then going to write your code, you're then going to test and debug it and so forth, and then maintain it. This is what I'm talking about here is what you actually need to do after when you start to write a program. We kind of talked about editing, compiling, but linking and executing are also important. And what I want to talk about here is the details of this. So these tasks are going to become second nature to you because you're going to be doing it every time you write a C program. You're going to be editing your source code. You're then going to be compiling. You're then going to be linking, and then you're going to be running. You're going to be doing this very, very often. So the processes of editing, compiling, linking, and executing are the same for developing programs in any environment with any compiled language. This is not unique to C. If you're writing Java, a Java program, you're going to write the source code. You're going to compile the source code. Linking you might not be as aware of in Java, but it's going to do some kind of linking. And we'll talk about what linking is. And then you're going to run the program. You're going to be doing all of this. What I'm describing here, again, is how it's done in C. So editing is exactly what you would think it is. It's the process of creating and modifying the actual code, the C source code. The C source code is going to be inside of a file, and it's going to contain all of the statements and all the instructions that you write. All C source code files end with the .c extension, and that's how you can identify that it's a source code file. Before that .c extension is going to be called the base name. You want to have your file names be meaningful. If you write a C program that adds 2 numbers, you may have a file called add.c that contains the source code. And remember that a C program, in most C programs, are going to have many, many different files. So your files should have good names. But the way that you can identify C source code is the .c extension. They all contain the .c extension. Now, when we edit our code for this class, we're going to use an integrated development environment. We're not just going to use a simple editor. An example of a simple editor would be something like WordPad. We're going to use something that has an editor, but also has many other things that help you write your code more efficiently. The IDE, and this is referred to as an IDE, Integrated Development Environment. The one that we're going to use for this class is code blocks. I'm going to cover in detail, but we're going to use code blocks for the editing task. But you can use whatever you want. If you want to use Notepad, if you want to use something even more minuscule, you can. Atom, there's Visual Studio IDEs, but the one we're going to cover in here is how to edit your code and code blocks. And this is a nice IDE, and the reason I chose it, we'll talk about in more detail, but it is cross-platform and easy to use. So editing is the basic process, writing the code. Compiling, we know what a compiler does. It just takes that high-level language code and converts it to machine language, and it also detects and finds errors in your code. After you edit your code, you're going to run the compiler. So the input to the compiler is going to be all of your source code, all of your .c files, everything that you're editing. And again, a C program can have many source files. But the input to the compiler are these source files. Compilation itself, converting this code, is a 2-stage process. The first stage is called the pre-processing phase, during which your code may be modified or added to. And the second stage is the actual compilation. It generates the assembly language code. And we'll talk about this in more detail, this pre-processing phase, but you just need to know now that there's 2 stages when you do compilation. The one that we're going to focus on, or the one that's easy to understand, is the generation of the object code. So the compiler is going to look at each statement, and it's going to make sure that the syntax is correct and that the semantics of the language is met. Syntax is to make sure that the structure of the code is right, that you have semicolons at the end of the statement, that you're using data types, that you're following the rules of the language. Semantics is the meaning of the words. So if you use an if keyword, that's a condition. Semantics happen in the compilation phase by creating a symbol table and so forth. But the compiler is important. It's going to generate this object code. It's going to tell you if you have any errors in your syntax. It can also sometimes recognize whether or not you have dead code, where basically code's not being used. It does not find logic errors. It only finds syntax errors. Again, syntax is the rules in the language. Logic errors are the meaning. Like if you made a mistake in logic, you may make a mistake in the functionality. So your code can run, it can compile, but it may not work as intended. And this is referred to as a logic error. The compiler is not going to tell you if you have a logic error. If you meant to ask the user for a number instead of a character, a string, or you ask the user for their last name before their first name, that's a logic error. Compiler is not going to tell you those types of errors. Typical errors reported by the compiler are going to be things like undeclared variables, expression that doesn't conform to the syntax, you don't have the right parentheses, you have, blocks that don't have ending blocks. You're going to become very, very familiar with the compiler errors and what they mean. Hopefully, after you've learned the C language and you run the compiler, you're going to see an error and you're going to be able to fix it immediately. You say, whoops, forgot a syntax, or whoops, forgot a semicolon. Oh, I forgot to provide a right bracket to end that block of code. It's going to become second nature. So after you fix all the errors and your compiling is successful, it's going to translate into assembly language and generate this object code. So the actual object code is a .o file. It's the actual assembly language code that gets run. It has an extension .obj or .o. .obj typically on Windows will be the extension. .o on a Linux or Macintosh system will be the extension. You're going to see that file generated after you compile your code. And that's just the end phase of the compilation. That's the actual assembly language. It's going to be binary. It doesn't look like text. You're not going to be able to look at it. It's just going to have a .o extension. And that's what the compiler generates. The way that you run the compiler in C is you actually use a command. You probably won't need to do this much because the IDE, the editor in the integrated development environment, is going to do it for you by just clicking a menu option. But it's important to know what's going on. So when you issue the compiler command, it's typically using a GNU compiler, which is a GCC command. But at the basic level, you just run a compiler program, either CC or GCC. You run that program and then you specify the input. Remember, the compiler takes as input the source files. You specify the input by using a -C flag and then specifying the source files, one after the other. So examples here are cc-c myprog.c, or if you're using the GNU compiler, which is a popular one, gcc-c. And if you omit the C flag, your program will automatically be linked as well, which is the next step. But really, it's easy to run that compiler if you're at the command line interface. It's even easier if you just use a menu option, which we'll probably be doing in this class. But again, it takes input the C source files. In code blocks, as I mentioned, you're going to be just clicking a menu option and it will automatically compile, link, and then you can click another menu option and it will automatically run. But again, what's going on under the hood is you're actually issuing the compiler command with the -C flag and the input source files. After you compile, you link. Like I said, every programming language has a linking, but a lot of times it's transparent. You won't even know what's happening. In C, the linking process is important because it's not always transparent. But with most modern IDEs today, it is. But I do have to emphasize that it is a little, it is important in C. So after the program has been translated into this .o code, this object code, it then is ready to be linked. The reason we link is if we're using external libraries, we have to grab all those other libraries and put them into one program. So linking is just getting all of the dependencies in place and building an actual executable file. So the .o file is the objects. You then link all the .o's into one executable. And again, this is usually transparent. It usually happens automatically when you compile. But again, it may not. And you may have to do a separate command, like a -L or something. But it takes all those object files and builds one executable. And the executable is what you run. So it's going to combine all of those, and then it's also going to combine, and you may have .os that are additional libraries, that other programs that you may want to use that somebody else wrote, or other libraries that come with the C language. You're going to take all of those and put them together. And the linking phase will also detect and report errors. They're two separate phases. Linking, again, will usually be like redefinition errors, or you're trying to call a function that doesn't exist. So if you don't have that .o file to make up the entire program, you're going to have a linking error. And you'll need to have all the .os. And again, the .os may not even be yours. They may They may come with the C language. They may be part of the standard library, or they may come with another program that somebody else wrote. But you need all those .O's to form one executable. So program libraries support and extend the C language by providing routines to carry out operations that are not part of the language. Input and output libraries are example. Mathematical libraries, string manipulation libraries. This is just the same thing. If you're familiar with the Java program, it's the same thing as the Java API. It's the same thing as packages. It's this concept of I want to write data to a file. I don't want to implement it myself. I'm going to use an existing library that comes with the language. It's still written in C, but it's not part. It's just C comes with that. So there's all sorts of different libraries that we're going to learn about and use. This happens part of the linking phase. So a failure during the linking phase means that once again you have to go back and edit your source code to make sure that you can find that object file. So a lot of the failures usually mean that you just need to include a file or something like that. This will become second nature as well. Success. If you're done compiling successfully and you're done linking successfully, that will produce an executable file. In a Windows environment, the executable file will have a .exe extension. In Linux and Windows, it will just have by default a.out. You can change the name of a.out to something more meaningful by just issuing something along with the compiler command. But most IDEs and code blocks as well will have a compile and link program in a single operation, and it will produce the executable, and then you can just double click the executable. Or you can run the executable from a command or from a menu option. But no, at the low level, if you're on Linux, you're going to see an a.out by default as your executable. On Windows, you'll see a .exe. A program of any significant size will consist of several source code files. I mentioned this earlier. Each source code file needs the compiler to generate the object file that needs to be linked. The program is much easier to manage by breaking it up into a number of smaller source files. You will want to use many source files, and you don't want a source file that contains 5,000 lines of code. That's not cohesive. That's not easy to manage. So you're going to create files that contain source code, and the source code is going to be specific. It's going to have a specific functionality. It makes it much easier to develop and much easier to debug, and is much more cohesive. So you're going to have many smaller source files. You don't want large source files with thousands of lines of code. And all these source files are going to make up the entire program. They're all going to have their own .O's, and they're all going to be input to the compiler. These concepts that make up the program essentially are also considered a project. You can think of it as that at a higher level. It's your project. It's your program. After you've finally done all of this and you've linked it and you've got your executable file, you can then run the program. In most IDEs, this is just going to be a menu click. Or you can double click in Windows. You can double click the exe. And if you're on Linux, you just type in a.out. Now, when a.out, you have to have certain permissions. So you have to maybe issue a change mode command. But to run it, you can say ./a.out. And that will run the program from the command line in Linux. But again, usually you don't have to worry about this. So the execution stage is where you run your program. Each of the statements of the program is sequentially executed in turn. If the program requests any data from the user, the program will pause and get that input. It can get the input via the keyboard, or it can get the input via graphical user interface if you have libraries for that in your C code. Results that are displayed by the program appear in a window called the console. And we're going to show you examples of this when we talk about code blocks. But when you run your program, typically you're going to see output. Not always. Sometimes programs will do things that don't produce output. But usually they produce output, and you see the output right on the terminal or the console. The execution stage also generates a wide variety of error conditions. So you may produce the wrong output, which is just a logic error, and you have to go back and edit your source code. It may sit there and just do nothing because you have logic issues. And then lastly, it may crash your computer, which is the worst case scenario, which means that you did something really bad in your program, and it was so bad that the program just died. Or it actually caused other programs on your operating system to crash your entire computer. Right? So running the actual C application can cause problems. If the program does not perform the intended functionality, then you have to go back and edit the source code. You may have to reorganize or redesign. And this is where we talked about the different steps. This is known as the debugging phase. to find and fix your errors. We're going to have a whole section on debugging because it is that important. I mentioned earlier that one of the best ways to learn is to learn through your errors. You're going to constantly go back and edit source code and debug. The entire process of compiling, linking, and executing the program is repeated until you're done, until you have all the results that you need for the functionality of that code. So here's again another nice illustration I like to provide. This is taken from a book called Beginning C by Everett Horton. But this is the process that you're going to have. You're going to edit your source code. You're going to create a file with a .c extension and a meaningful name. You're going to use an editor to do that, or an IDE, integrated development environment, something like ColdBlocks. You're then going to compile it. The compiler is going to generate an OBJ file, an O file. If it doesn't generate that file, that means you have errors and you have to go back and fix them. After you create the OBJ files, the object files, you then have to link them all together to create an executable file. And you could also have errors in that phase where they're not linked properly. You have to go back and edit your source code. Once you actually have no errors and you have an executable file, you can then run your program. And again, after you run your program, you still may have errors because there could be logic errors. So then you would go back and edit your source code. So this is going to become a repetitive process that you're going to be very familiar with. Edit, compile, link, execute. And this again is typically what you do in all languages. You're going to be doing this over and over and over again until your program meets all of your requirements. Yeah.